Are you ready, Professor Milonchikov?
Yes, yes.
Okay, thank you very much. So it's my great pleasure to announce our today's speaker, Professor Dmitry Millionschikov, and the talk would be the characteristic algebra of Klein-Gordon equation and higher symmetries. So please, thank you very much, and please go ahead.
Okay, thank you very much for your kind invitation. It was really interesting because I never been in Rostov-on-Don, and this is maybe first possibility to make a talk at your university. And unfortunately, while waiting, I found two misprints. The first one is in the title, in the word of characteristic, stupid misprint, and another one is just you have changed the order Gubkin Oil and Gas University. But I hope that it's not so important, just I'm just curious. Okay, so just all the things that I'm going to talk today is my talk is based on our joint paper with Sergei Smirnov, my colleague from Moscow University, and it was published in UFA Math Journal last year. Here it's coordinates and just some explanations, how to say, personal explanations. Because why UFA journal? It was important because of higher crucial contribution of UFA school, mathematical math physics school, to this subject. And last year it was some important dates. First one was 40 years from appearance of preprint by Alexey Borisovich Shabat and Ravil Islamович Yemilov on exponential systems, and also sad events that happened. It was Alexey Borisovich and Ravil Islamовich passed away 2 years ago, and the last, I mean, that's very sad news that happened in March this year, that Anatoly Vasilievich Zhiber also passed away. So, you know, that last years were, in some sense, hard years that a lot of people. So, but anyway, there are still have a lot of activity in UFA school, young. The students by Shabat, Zhiber, Yemilov. So I hope that everything will go on with this subject. But anyway, I want to, to pay special tribute to the impact to this subject. And I mean, the most part of the things that I'm going to talk today is based on the papers, books, and so on, and maybe I add only just a few not important steps in this direction. So let's start. Also, yes, that what's going is not said, that still our colleagues Vladimir Sokolov, Всеволод Adler, Ismail Habibulin, and his students, Maria Kuznetsova, Regina Murtazina, as well as Rustem Garifulin, maybe Alexander Mikhailov, and not from UFA school, but there are a lot of people that, but for today, I stress, point out the contribution by UFA school and important people from UFA. And just to start with some elementary effects that I want, you know, that maybe my talk is not in mainstream of your seminar. It's far from functional analysis, unfortunately. So there are more algebraic stuff and from geometry also. But the meeting point is differential equations, so the very important field. And here I hope that we need to use all mathematics we have just to obtain important, interesting results. So just to start with some elementary things, just recall the material of the standard course of partial differential equations. They're very simple. It's wave equation in a very simplest form. Everybody knows that if you take characteristic variables, then your equation can be rewritten as vanishing second order derivative uxy. And of course, it's obviously we got a formula for general solution. It's a sum of two arbitrary functions on one variable. One of them, first psi, depends on x, and the second one, phi, depends on y. And just how to say, not a deep remark, but just important for the future. So just how we can look in a view way on this equation. So if you take expression that I denote f1, it's partial derivative of first order ux. So if you take solution u of our equation, wave equation u, then the property holds the last line. So the partial derivative of f1 vanishes. So this is just a remark. Okay, so this is very elementary things. In some sense, we're going to tell just also elementary, how to say, very naive approach, not naive, but important approach and naive. So those of us who are giving courses in standard course of higher mathematics, but for me it's more than Gubkin University. Everybody know just a part of our course which deals with differential equation of first order, and in fact what we do with students, just in some special cases we write out formulas for general solutions. So, and there are several types, and depends on the level of students or the level of your course of mathematics. But anyway, it's standard procedure just to write out explicit form. And now we are working with partial differential equation. So you see that instead of wave equation, I replace 0 on the right hand part by exponential u, and this is also famous Liouville equation. Of course, there are a lot of formulas. If you look through, for instance, in Wikipedia, there are a lot of formulas concerning Liouville equation, different expressions. But for today, the Liouville equation will be is the first line. It is written as the first line. So it looks very elementary. And the classical general solution formula, in some sense, is related. You see, again, we have two arbitrary functions, psi and phi, and we do not just to take account no, how to say, it's not Cauchy problem, no initial conditions. So it's just a kind of, how to say, algebraic result. So if you just formally take second order partial derivatives, you'll have this equality. I mean, this is solution in some sense. So of course, if you have some conditions and just some restriction on property for functions, that is very hard problem. But formally, Liouville himself found this expression, which, for instance, we use in differential geometry. I remember several times that in Liouville metrics and so on, we met a lot of times this formula. And again, the remark for today that if I take this expression, now look more attentively, I denote it by f2, and it equals to second order derivatives uxx minus 1/2 ux squared. And if u is not arbitrary function, but just an arbitrary solution of our equation, Liouville equation, its partial derivative with respect to to y vanishes again. And this is, you see, very simple computation that is absolutely elementary thing. Just you replace, you see that in the third order derivative uxy by the formula by exponent, and it is evident that this expression vanishes. So you see this in wave equation we have f1, it was first order derivatives, but here we have expression in some sense quadratic, because you see the second order and minus 1/2 derivative squared. And now just I want to recall that Klein-Gordon equation for today, it is just generalization, general form, when not necessary to have exponential on the right hand part, just an arbitrary function. And again, we the classical, of course, expression like in physical applications, just it's another expression. But for today, I use characteristic variables, like in the case of wave equation. So for today, Klein-Gordon equation will be uxy equals to some function on u, on one variable. So this is, but the main difference, you see that here the wave equation was linear, so we can just apply all techniques of Fourier series and a lot of other things. But here it's a non-linear equation, so it's just quite different story. And now just I want to remember my first remarks concerning expression f, which involves u and partial derivatives of different orders of u with respect to x. You see that u, uxx, uxxx, and you see that is no u. It is very hard. So maybe it is last time when it's possible to write u 3 times x, and after fourth order is kind of disaster to write out all partial derivatives. So it's quite natural thing just to change a little bit notation. Instead of ux, you write u1. Instead of ux, you write u2, and so on. And this is simplifies your formulas in an obvious way. And I call not me, but it's classical definition that is going to Darboux, back to Darboux, that a function which depends, and also a remark important, that you see that I have not fixed the order of derivatives of the expression. But however, it can be arbitrary, but not infinite sequence, just some finite number. And it is this function is called x integral of the Klein-Gordon equation. If you remember our examples, its partial derivative with respect to y vanishes. Obviously, that if you remember our examples now, q2 instead of f2, maybe it's not good idea to change notations. However, it's q2, and you see that instead of uxx minus it's a misprint. Okay, I missed 1/2 here in the formula. So of course you have to restore 1/2 u2 minus 1/2 u1 squared, and this is, again, just recall, this is integral of Liouville equation. Again, I just recall this very elementary computation. And now, just to explain other important examples of Klein-Gordon equations, just want to recall systems of exponential time. Now you have not one variable, you have a vector. You see that w, which is now plays the role of u, in previous slides, it's a vector with coordinates with upper script j, 1, 2, r, so r coordinate vector. And its the derivatives depends also, you see, the exponential on some linear expression in W. Just you see that for in case of two-dimensional case, r equal to 2, and you see there's a system that your both coordinates derivatives have second order derivatives wxy1, it's exponential but with some linear combination of w's, and the same story to the second component. And the matrix of coefficients, which is denoted by A, is so the matrix is its constants. And I have just, of course, you have, like in the Liouville case, that in general, in arbitrary matrix, intuition tells you that no sense to expect explicit formula. So there is very popular object like Carton matrices. I hope that everybody knows it because it was part of classification of simple Lie algebras. Here I present non-degenerate Carton matrices. You just remember that we have two on diagonals, some conditions of 0, and you have possible values on non-diagonal entries, -1, -2, -3, -4. And just to recall, if you take the classical result that I have no time to discuss, that the same, not the same, but also like in Liouville case, you can explicitly integrate the systems with these 4 Carton matrices. And the first one, you see, you have a diagonal matrix with 2 on diagonal. This is obviously, it's 2 times Liouville equation. So you see that if A1, 2 and A2, 1 vanishes, this is exactly Liouville equation, but with a slight difference. We have multiple 2, but it's not essential. It can be, you can change coordinates very quickly, and it will be, you'll have 2 Liouville equation in our form. But interesting case for today is so-called degenerate Carton matrices. And this is how 50 years now, yes, 50 years ago, it was very popular subject. It was so the theory of Moody Lie algebras or fine Lie algebras. And now just if we consider our exponential system, the remark is that we can decrease the number of variables. So if your last line in your Carton matrix is linear combination of first n minus 1, so you can change, you can replace, you can introduce new variables. Now I denote it again by ui. You see, you just replace this linear combination by corresponding ui. It's not power. It's like in differential geometry. You see, maybe I had to tell you earlier, but I just recall that it was tensor notations, and the indices of coordinates I put as upper scripts. It's, for instance, ui, it's not u in the power I, it's I coordinate. Maybe for differential geometries, it's a standard way to work with coordinates. And what we'll have? So we have reduced system with one less equation. But it's not, of course, interesting in for large n, but for n equals to 1, the two-dimensional case is really interesting. Now let's consider the following degenerate Carton matrix. In fact, we have two degenerate Carton matrices. It's one of them. You see this? And if we use our method, we'll get one-dimensional equation. And what we'll get is very important two cases. So two Carton matrices and two cases. So if you in this case for this Carton matrix, we'll get so-called Klein-Gordon or hyperbolic Klein-Gordon equation. So in this form, the multiple 2, which it stands before exponentials, it's not sufficient. We can remove it using some coordinate changes, does not matter. So just and the second degenerate Cartesian matrix is, you see this 2 minus 4 minus 1 2, and this is so-called Tsutseika equation. And Tsutseika, it's interesting. It was in fact it was very, how to say, it's really understanding mathematician. He was maybe I forgot, he was maybe student by Darboux, and he was, and I read that he was the responsible geometry sessions on 3 international mathematician congresses in 20th. So it was he had very strong school, and he was a specialist in differential geometry, and everybody knows in theory of surfaces of constant curvature the role of Klein-Gordon equation, but Tsutseika used his equation also for some reason of the differential affine geometry. So I no intention time to say more details about it. Now it's that how to say is used like Tsutseika equation. So maybe for me it's always a kind of problem to write out correctly his name in English. In Russian, it's how to say, like Shubeka, Tsutseika, but in English, I hope that there is no misprint now. And these are both very important cases of Klein-Gordon equation. So just explanation, because Carton matrices, I recall, is related so-called of root systems as special vectors like Coxeter groups and so on. It's like a kind of miracle. So Carton matrix is related to geometry very strongly. And definition, just recall our first definition of X integrals. Now we generalize a little bit our situation of Klein-Gordon equation. Now I allow my right-hand side function f to have dependence on variables x, y, u, and as well as first derivatives u, x, and y. Of course, you can consider more complicated case, but even in this situation, it's not very easy to study a general case. And the definition is called Darboux integrable if admits both x and y integrals. Just remember our first case of Liouville equation. That was very nice. And for the Liouville equation, we got everything. We got everything. We got explicit formula for general solution for x and y integrals, and everything was possible. But the theorem by Alexey Borisovich Shabat and Anatoly Vasilyevich Zhiber from 1979 that the Klein-Gordon equation is Darboux integrable if only if function f can be reduced to exponential. I don't want to explain what does it mean explicitly can be reduced. In some sense, by changing the changing variables, changing the coordinates x, y. Remember, we started with changing characteristic variables. So there are some hidden possibilities how to not. It's rather flexible right-hand side, but in fact, integrable only Liouville case. But what is interesting that there are another kind of integrability that we're going to discuss today. So the existence so-called Lie-Backlund group or group of symmetries. I will try to explain what does it mean. If you extend your Liouville at two other cases. Remember that was Klein-Gordon equation and Tsetsek equation. And the classification of the case of 4, I mean, the answers, what about integrability, was done by Vladimir Sokolov, Alexander Mikhailov in 80th, but it's how huge a list, and it just very complicated. And in fact, there are some doubts that there are no mistakes in classification. I am not, how to say, personally is responsible for the answers, but I had some, how to say, positive attention answer or negative. So it's very interesting. Now I want to put maybe it was elementary introduction that was understandable. I hope understandable now. And so I try to introduce more algebra in my stuff just to define the main object for today, the so-called characteristically algebra. So remember that, of course, it's a kind of miracle if you if it is possible to write down explicit formula for general solution. Oh, by the way, so Tatiana, I forgot how many time I have for my talk. 1 hour and 1 hour and a half.
1 hour just.
1 hour. Okay. So maybe I just late. I skipped some slides, and just I want to fix notation. Remember, please remember this definition of x integrals, Darboux integrals, so-called Darbouxins. It were the expression of the kind that you have expression depending on u, ux, uxx, or now u1, u2, u3, and so on. And u now is an arbitrary solution of Klein-Gordon equation. So not arbitrary function, but a solution. And in this situation, you want to apply partial derivative with respect to x, and I denote this operator by capital D, capital letter D, to the function like g. You see gxy, and g, which in fact is expression depending on u, u1, u2, u3, and so on. And if I formally take this partial derivatives, it's a standard formula of differentiating of complex function. You've got this formula for operator. But if you look on algebraic formulas, you see that it is more convenient to immediately to introduce our new notations like u1, u2, u3. You see that partial derivatives du with respect to x, it's u1. Partial derivatives of u1, it's exactly u2, and so on. So it looks like polynomial differential operator of the first order. You can now, from some time, forget about how we got these coordinates u1, u2, u3. This is first order polynomial differential operator. It's kind of shifting. You see that it's, if you apply this operator to u1, it goes to u2. In some sense, it shifts your coordinates. And the same story, not the same story, but analogously, if I try to write in a new way the operator of partial derivatives with respect to y, you see that this formula will have this, what we have. And important remark that I can divide into parts our formula. The first term, you see, that is uy times to operator d over du. And I denote this operator by x0 as it is written on my slide. And the whole tail, you see this operator I denote by xf with downscript f. An explanation why I wrote xf is below. You see that when I reply, now I recall that u is not arbitrary. It's solution of Klein-Gordon equation. So I can replace uxy by function f. That's why we have here f, and then in fact you see this is operator d applied to f, d squared to f, and so on. So this is the sum of two operators. And of course, if f is integral, it have to be annihilated by, if f function is annihilated by both x0 and xf, then it's x integral of Klein-Gordon equation. And in fact, it's not obviously how to find and whether they exist and so on. So we took in our examples. And what about characteristically algebra? So you see that two operators which annihilated by function f. And the definition of characteristically algebra, if we have two operators, xf, x0, which both of them annihilates Darboux integral, then all their brackets, all their commutators as differential operator also vanishes on Darboux integral. So the whole Lie algebra generated by two these vector fields, two first order linear operators, is must be annihilated by Darboux integral. And why it is useful, we'll see later, but you see that it's the, how to say, sometimes it's a huge family of operators of different orders, or of the not orders, first order operators, but different gradings. We see some weights and gradings late. And the initial was idea that of Boursa, who was in fact, there are some humors. I remember that Boursa was in fact real author of Fichtendoll's manual of calculus, and Fichtendoll's translated in Odessa Boursa course, but I'm not corrected personally. So Boursa, of course, it's outstanding French mathematician. So it was a long story of the beginning of the century. And what about examples? So the first example, we started with Liouville equation. What about characteristic Lie algebra for Liouville equation? Just remark that commutative x0 xf, if you calculate by hand, you see that it is this operator of the same kind, but you replace f by its derivative with respect to u, or ordinary derivative, standard derivative, like a function of depending on one variable. And if f equals exponential, it's obviously that commutator is again the same vector field. And this is well known two-dimensional solvable Lie algebra. And the only one non-trivial Lie algebra in dimension 3. And of course, we have a lot of symmetries, we have a lot of integrals, we have, so it's not, how to say, miracle, just waiting. But in general case, it's not obviously that what will have like a Lie algebra. It can be happen that it'll be infinite dimensional. So finite dimensional is kind of miracle. But again, just or maybe the same slide, but okay. Okay, it again. Now, what about second interesting case, hyperbolic Klein-Gordon equation? You see that if I take my x0, but I denote here xf by x1 because instead of sign, and so standard formula that the first commutator will get x of cosine, and if you again apply x0, that we again get x sine. So the adjoint operator x0 has the very simple formula, 2 by 2 matrix with entries like 2 zeros, 2 ones. And I can consider 2 eigenvectors of this operator, which in fact is our, we made them in Liouville case, the operator x exponential and almost the same, but exponential has minus u. And again, sorry, so I have to go further. And of course, there are other papers studying the properties of Lie algebra. It was Ismail Habibulin, Murtazina, and maybe other student of Ismail Habibulin, who in fact was now one of the leaders in this direction of symmetry approach to differential equations. But my first result in this direction was the theorem that 2019 that Lie algebra of Klein-Gordon equation is a affine Lie algebra, so-called A11. Does not matter what it means if you have no. You see, one can look commutator relations of operator. So it has infinite basis. I denote it by x prime y. You see, this is periodicity with respect to 3, and the commutators have very simple forms. We have only 3 cases occur. So coefficients 1, 0, and minus 1, and it depends. And this is well-known algebra of okay. It's affine Lie algebra. I have no time just to go to detail. In Tsetseka case, we'll got Lie algebra A2. Why it was useful? Because there is a last ingredient of my talk, so-called higher symmetries, I need to define, and now it's definition. So instead of your initial equation uxy equals to f, you consider so-called linearization of this equation. Now the function g is called higher symmetry. It satisfies this equation. I hope that you remember the definition of operators d. That this is partial derivatives. You remember this operator. And there were important results concerning Darboux integrability when, in terms of so-called Laplace invariance. Also, I have no intention to define them. But Zhiber and Murtazina show that if we have Darboux integrability, your characteristic Lie algebra must be finite dimensional. This is very, very important observation. Okay, why it is. So, what about general remarks? What does it mean, integrability of hyperbolic systems? I recall that in the Liouville case, we have everything possible. So, explicit formula for general solution, Darboux integral, symmetry, so on. but it you remember, it's just kind of miracle. So more realistic approach, if we have Darboux integrability, the set of integrals, just consider this case, the existence of so-called high symmetries, just definition, why it is here, high symmetries. We just discussed how to obtain, how to find integrability. Or integrability is school of Novikov, Shabbat, Zakharov, that integrability in the sense of inverse scattering method. Today, I will say nothing about this approach. No inverse scattering method. Although there are some, how to say, relations, but not direct, just coincidence. The results. The answers depends when you go, compare the answers. You think that it is some kind of miracle because both cases, Tsitseka and Klein-Gordon, are integrable from the point of view inverse scattering method. Klein-Gordon is classical result like Korteweg-de Vries equation, and Tsitseka integrability was proved by Alexander Mikhailov. It was classical result. And now we talked about Darboux integral again. And just I want to, it's a lot of dull things that I told, but here it's kind of, I try to very naive illustration, maybe more than, very, very naive. You know, that is, here is some in Russian. I forgot to replace. Okay. And you see that is not partial, the equation, not in partial derivatives. First order differential equation. It's the same that I gave the students, last session. It was in linear equation, standard linear equation. Even in all technical departments, students have to solve this equation. It's possible, we know this procedure. But here, what picture means? You see that what is the plot means? You consider you have three coordinates in this plot: t, the time, y, and y dot. The derivative with respect to t that we consider as a independent variable, like z, or not z. It's y is like that, t is kind of x, and y dot is y. And if you just replace t by coordinates, in fact, this is second order algebraic surface. You see this saddle surface, it means that hyperbolic paraboloid, maybe a little bit rotated. But the idea is, of course, I mentioned that this standard equation, even student from the technical department has to find this general solution. This is the formula, is the last line. But so it is, how to say, the strongest possible case when you have explicit formula for general solution. But here we have some to weaken approach. You see that we have one parametric symmetry group which acts by this formula. So you multiply t by exponential EA, y by EA, and so this is group of symmetries. And if you have group of symmetries of your equation, you just can move arbitrary. If you found some solution, you can move along this action of your parametric group of symmetries. You've got other solutions. This is, how to say, idea. But sometimes you have no your group, one parametric group is given by vector fields which are tangent to the lines of your transformation. And symmetry in some sense, but you know that if you deal with hyperbolic equation, we're living not in three-dimensional space, but in a space of arbitrary dimensions, so U1, U2, U3, and we are looking for some Lie or Lie-Backlund group of symmetries acting on your space of your solution. So if you have you're lucky to find one solution acting by your group, you can get other solutions. That was a non-formal idea. Again, what's happening? I go. And what we get, what we have, what about high symmetries of Klein-Gordon equation? So our equation for high symmetries is written, looks very simple. So high symmetry is a expression f depending on ux, xx, and so on, which satisfies this equation. Now again we return to our, how to say, most important and elementary example of Liouville equation. And you see that, what about operator x? You see that interesting combinatorial remark that everybody, I hope, knows that Bell polynomials, very useful, and maybe in course of calculus, you remember Faraday-Bruno formula of higher derivatives, and if there are Bell polynomials that hidden inside. So the expression, the coefficients, polynomials standing before operators in this series are Bell polynomials. And you remember that we already found one x integral of the Liouville equation. It was u2 minus 1/2 u1 squared. But we can get new polynomials. You see, just we can apply operator D to operator to F2. So U2 goes to U3, and when D applies to 1/2 U1 squared, it's derivation. So 2 annihilates with 1/2, and we got U1 times U2. Then next polynomial, again, we consider D squared applied to F2. It will be the polynomial of U4, no, combinatorial polynomial U4, U minus U2 squared, and so on. And the theorem proved by Shabat and Gibber in 1979 that all integrals of Liouville, there are a lot of integrals, of course, but all of them, in some sense, like F2 is kind of Adam of our mankind of X integrals. So everything one can obtain from F2. So it is subalgebra generated by the polynomials F2, F3, F4, and so on. So, or like in differential algebra, so F2 generates all our differential subalgebra. So this is essential integral that we see. And what about higher symmetries? So we have two types of integrability, either x integral, Darboux integral, or higher symmetries. And if we write down the equation of higher symmetries, you immediately got this equation in differential equations, and it's combinatorial, completely combinatorial. You can even find these formulas in the book of Riordan called Combinatorial Identities, in the chapter devoted to Bell polynomials. And the theorem proved by Shabat and Gibber that an arbitrary symmetry can be easily obtained from some Darboux integral. You have to just apply D plus U1, its multiplication by U1, to some integrable. For instance, if I apply d plus u1 to our, how to say, Adam, f2, then the resulting polynomial will have the form u3 minus 1/2 u1 cube. And in fact, it's when we pass to Klein-Gordon equation, you have, you see that in the case of Liouville equation, we have a lot of integrals, either symmetries, either integrals, the huge subalgebra. But Klein-Gordon, the situation dramatically changed. So we see that there's some, how to say, the system of equations that we have x integral is, we have no x integrals. This is a result by Shabati-Gibber. But what about symmetries? Not a lot of symmetries. So it's easy to see that to find first symmetries. First one is u1. It's just, I recall it was first derivative, ux. u3 minus 1/2, we already discussed. But what about others? And the observation, what is the role of Lie algebra? So not crucial, but very important. So you see that is using two generators of Lie algebra, you can shift goes between different symmetries. So of order, if you apply x1 prime, x2 prime to symmetry of Fn, I obtain symmetry of not order but of power n minus 2. So in fact, even he obtained, how to say, some recurrence formula, how to get all the chain of symmetry. So this was symmetries. And okay, so Klein-Gordon symmetries. Yes, and also I have now the time, so I have to skip. It was the same, the result, more complicated formulas for Tsek equation, more specific answer, but also the description in some recurrence sense. But what is the relation to Lie algebras? Maybe the most, how to say, complicated part, but I have 5 minutes to have 5 minutes. It's related to the notion of so-called growth of Lie algebras. And just if you have finite dimensional algebra, feel safe, it is growth rate of growth 0. It's okay. So the growth non-trivial has infinite dimensional Lie algebras. And if we remember that our characteristic Lie algebras were generated by two differential operators. Generally, your Lie algebra is generated by not two, but some finite dimensional subspace V1. In our case, two-dimensional examples, but generally V1. Now we consider the span of all brackets of first order of letters of generators of your space V1. And it is subspace that I denote V2. Then I add all the spans, consider span of all second order brackets, second order commutators, and so on. So you have increasing chain of subspaces in your Lie algebra, and in some sense limit is our Lie algebra. And I just introduce growth function. Just dimensions of all our spaces, because your initial space V1 was finite dimensional, so the same story is with other subspaces. And of course, it depends on the choice of your initial set V1. There is several ways to define the notion of growth. The accurate depends, so it's some stuff you should that is grow the notion of equivalence of different growth functions, complicated. Another one is so-called Gelfand-Kirillov dimension. So it's maybe not clear formula, but in some sense it's your growth, if Gelfand-Kirill dimension finite, your dimension grows like n in power Gelfand-Kirill dimension alpha. So this is some sense growth. But there are special cases of so-called Carnot or natural graded Lie algebras, when your Lie algebra is just, how to say, have graded, is this direct sum of subspaces, which satisfies the property commutator of GI with GA lies in GI plus J, and so graded. And in naturally graded case, you have this condition, Carnot grading, is a special grading and special Lie algebras. In this case, the growth can be defined, can be more, how to say, naturally. So this the diagrams showing how fast is the growth of our two Lie algebras, and one is related to Klein-Gordon equation, and two is related to Cicek equation. Growth means how quickly your dimension increases. So the n in n1 grows faster than n2. So n2 slower grows. Although from natural sense, the height is quite natural, but growth is number of, how to say, number of bricks in these diagrams, depending on the space. Opla again, good. And I have last 2 minutes and just remarks. And the growth, okay, just I skip the result on Lie algebras, does not matter. And the fastest growth is free Lie algebra, so it's exponential growth. So slowest growth, it's special Lie algebra, we have no time to discuss. But the rates of growth of our Cicek and Klein-Gordon is 4/3, 3/2 rates respectively. And of course, the natural question, I have the last minute, what was, because it's kind of very classical things, what are, how to say, new results, some perspective of investigation. Yes, it was everything, in fact, now is known for Liouville, Klein-Gordon, or Cicek equation. But the question is still a lot of questions in explicit formula for higher order, high dimensional analogs of exponential systems. Just I put maybe one result of my colleague. It was also in the article I mentioned above. And you see that if I consider the exponential three-dimensional system with a matrix, it grows has 8/3. And you see this is, how to say, periodic structure of its basic elements. And it was open question. Gibert found explicit formula for higher symmetries, or I mean group Lie-Backlund generators of group and symmetries. But in high orders, there's still a lot of questions. Sergei Smirnov managed to find explicit formulas for symmetries in Carton matrix. What about, how to say, other perspectives? It's because otherwise there is no sense to make a talk. I think that the Carton matrices and their relations to geometry, to simple Lie algebras, I mean the theory of representation, I think that one should continue to find explicit formula for symmetries of equations in terms of representation theory of corresponding Kac-Moody or fine Lie algebra. But it's, of course, it's completely another story. Maybe I hope, my strong hope that it will be possible in the future. That, however, it's some, how to say, it's kind of fog, London fog, which are direction, but I mean that intuition, or how to say, Carton matrices, it's not by occasion. So you should have something, your answer, you should have answers more evident from combinatorial, from a mathematical point of view. So the aim is to find good formulas for higher symmetries, for other Carton matrices, other exponential systems. And of course, natural question, it's pure mathematical thing. What about application? If you see the papers by Andrei Liznov or Savelyev, there are in introduction explanation in what kind of physical problems one can meet exponential systems. And there are some superconductors, I remember, some other plasma problems with plasma equation, and so on. So, in fact, it is there are applications. Of course, a lot of formulas were already obtained, but I mean that if you have nice expression for higher symmetries, I mean combinatorial, or from the point of view representation theory, I think that it will anyway simplify all calculation with it. So this is the aim, and maybe I'll stop here. It's just 1 hour, yes. Thank you for your attention.
Thank you very much for very nice
maybe
talk.
I have slide with thanks.
Okay, we can wait.
Thank you. Thank you.
Okay, thank you. Thank you again for very nice talk. And we have time for questions, please. You can raise your hand, or you can just go ahead and ask your question.
Okay, just.
Well, maybe I'll have just a general wondering. What about the method? As far as I understand, this method works well for the case of hyperbolic equation, or there is no difference?
Only for hyperbolic. I mean,
only for hyperbolic.
Yeah. Because it's algebraically. We seriously use the simple expression when we replace second-order derivatives by function. It was essential. I mean, from combinatorical or from algebraic point of view, it was essential. Of course, you see that all that I told today, it was a completely algebraic stuff. It's not, you have no functional analysis. Maybe fortunately, maybe unfortunately, but this is the story. Anyway, I think that, I mean, differential equation is the field, I just say again, is a battlefield when we should use all methods of modern mathematics.
Yes, but you see, when you start to put together differential equations and geometry, you may think about just 3 types of different cases of geometry: hyperbolic, parabolic, and elliptic. And then you can think just to apply hyperbolic geometry to this hyperbolic case. And that's what I thought, because I'm not an expert in geometry. So, but I understand that this method works only for the hyperbolic one. Okay. And maybe one more, maybe stupid question: if there is a chance to use fractional derivatives in this calculus?
Oh, honestly speaking, I have no answer. I think that you know that from the point of view of today knowledge, I have no idea. But how to say, my experience that you should never say that it's no idea. Sometimes, you know, a lot of examples, then you suddenly you understand that you should use it. But
yes, because you mentioned applications and also liquids, etc. You always find this fractional calculus and equations.
But in fact, myself, I say that I'm not expert in fractional calculus. Maybe I remember of one talk by Vasily Kolokoltsov several years ago. Yes, when we discussed. But after that, nothing happened. So maybe Yeah, maybe, but no idea.
Well, just a general question. I see a hand by Vagib Guliev. Oh, please, Vagib, go ahead.
Thank you. What my question is as follows: about Sobolev estimates for hypoelliptic operators on homogeneous Lie groups. You investigate or no?
You mean hypoelliptic?
Yes, hypoelliptic operator in homogeneous Lie groups.
Yeah.
As a direction, Lancanelli, Italian mathematics, and so.
Yeah, but no, I have not yet studied, but now I am dealing. But to my mind, it's not two things that the only relation that they use the same Lie algebras. But unfortunately, how to say, to my existing knowledge, I have no other, how to say, connections. I mean, now I'm also, yes, you're right, interesting that
regular solutions.
Yeah, but I cannot answer. Maybe I should look how to say, thoroughly think about your question, but I never thought about this direction. This is
okay. Thank you very much.
Thank you. Okay, so more questions, please. Joel, please go ahead.
Hello, Professor. Do you have maybe the article published in 2021 in English? Because I am looking here and it is in Russian.
Yes, but I think that to fudge, I have other references, I mean, which is close to this subject, but UFA journal is it translated to English.
Oh, that's good.
It's open source. Open source. You should go to the site by UFA journal. I think that there are all volumes are there as a open. No, you can, for everybody is open, and then as well as English translations. If you will have some problems, please just maybe Professor Karapetyants can provide you with my email. I'll send you immediately.
Thank you very much.
Yes,
really appreciate it.
Yes, no problem. Okay, more questions, please. Well, if there are no more questions, then let's thank speaker for very nice presentation and talk. Thanks to everyone who attended our seminar and